Hello. In this video we're going to look at a new topic, the idea of probability. We're going to start out with some definitions of what the different things are that we're going to be using when we're studying probability. And then we're going to look at some basic examples to give us an idea as to how it works and what it is. And it's basically just a way of measuring what the chances are of something happening. It's used quite a bit in our lives around us, and so it's nice to have an idea as to what they're talking about when they say the odds of something are this, or there's a 20% chance of that, or whatever. So let's go ahead and get started with the idea of probability. So here are the notes from Blackboard, and this chapter is split up into two pieces. And so I want to start off in this section by looking at some of the basics of what probability is. And in order to do that, we need some definitions to make sure that we know what we're talking about when we start using some different terms that you have maybe not seen before. So the first term we're going to talk about is the idea of experiment. And an experiment, we're going to say, is any observation of random phenomenon such as rolling dice, picking cards, tossing coins, etc. Okay, there's lots of different things that we can use when we're looking at different random phenomenon. Okay, the outcomes, those are the possible results of an experiment. So if our experiment is rolling dice, then those results could be, if we're rolling one die, you could get a 1, 2, 3, 4, 5, or 6 if we're dealing with a six-sided die. Or you could look at the sum of two dice. If you're rolling two dice, you could get 2, 3, 4, up through 12. Or if you're picking cards, you could be picking face cards. You could be picking red cards. You could be picking aces. Okay, lots of different things. If you're tossing coins, you could be getting heads, tails, okay, all those sort of things. So those are some ideas of outcomes. The next thing that we want to define is the idea of a sample space. And a sample space is just the set of all possible outcomes. Alrighty? It's a set of all possible things that could happen when you're doing your experiment. An event is a subset of a sample space. And what I mean by a subset is it's just some of those outcomes. So let's say we were playing craps, alrighty? And in craps, maybe an event space that we would be interested in is rolling 7 or an 11. Okay, and that would be our event space. Notice there's a lot of possible outcomes. We could have anything between a sum of 2 and 12, but we might only be interested in the 7 and the 11. The probability of an outcome is some number between 0 and 1. And we'll talk through why it's in that range in a little bit here. But it's some number between 0 and 1. And we say that the number 0 represents a probability of something not being possible. Alrighty? So the probability of, let's say, me being in New York City this afternoon is 0. That's not possible. Alrighty? 1 would be sure to happen. Alrighty? And so, the probability of me going on to number 6 is a probability of 1. It's sure to happen. Alrighty, let's go on to number 6 then and figure out what the probability of an event is. So here's the probability of any outcome. Could be anything between 0 and 1. But the probability of a certain event, we actually have a formula for it. We say probability of some event E is equal to the number of ways the event can happen over the total number of possibilities. Or we have a fancier way of writing that. Our fancier way of writing that is we say that the probability of some event E is the number of ways that E can occur over the total number of ways, which would be the number of ways that the sample space can occur. Now notice if there's no way that E can occur, you get a 0 over some number. And so that would simplify down to 0. And that's a not possible situation. If you have the number of ways that E could happen is the same as the number of total number of possibilities, then you have something that's sure to happen. Alrighty? Okay, so that's the formula we're going to use as we start working through the idea of probability. So let's look at a couple of ideas here. One is called the empirical assignment of probabilities. Now there's two ways that you can look at probabilities. You can look at empirical probabilities, which is basically when we do an example and we just run through it and actually run the example. And the other is what we call the theoretical probability. And that's what we think should happen given ideal circumstances. So the empirical assignment is basically collecting data to find a probability. Okay, collecting data to find a probability. And what we're going to do is, again, it's going to be the probability of that event is going to be the number of times that that event happens over the number of times that you do something. So let's say that I was to roll a die. Okay, if I was to roll a die and I was just to keep track of what was happening, and I got a 1, and then I got a 5, and then I got a 3, and then I got another 3, and I got a 5, and then I got a 4, and then I got a 6, etc., etc., etc. Okay, you would keep track of how many times you did that experiment, and then how many times you rolled, say, a 1. Okay, and those would go in those two places for empirical probability. The other way is theoretical. And that's when you're just calculating the probabilities based on what should happen. And in order to do that, you need to have something that we say is equally likely. All right? Very important that we have something that's equally likely. And one quick example of that is, let's say you're rolling 2 dice. Okay? If you're rolling 2 dice and you say that your event is a sum of 2, that's not something that you could use when you're looking at probabilities unless you're real careful with it, because you have a worse chance of rolling a 2 than you do of rolling a 7. All right, so you have to be real careful. But again, it's going to be the same thing. Okay. So actually, maybe up here you could say, instead of this formula, we could say that the probability of event E is the number of times E occurred over the number of times the experiment was performed. Experiment was performed. And then down here, if you're doing it with theoretical, you're not actually running the experiment. You're just saying, well, if these are all the possibilities, these are the times that those different things will occur. And we'll look at some examples of that as we go. So let's go to the next page here. And we said last time that it was very important that we had something that was equally likely. Because if we try and calculate probabilities when the outcomes are not equally likely, we're going to get the wrong example. And so we need to rethink the experiment so that the sample space has all outcomes that are equally likely. Now, the best way to illustrate that is to go over here to the computer, and I'm going to go to the Blackboard site. And for the Blackboard site, I'm going to go to the chapter folders. I'm going to go into the weeks 8 through 10, chapters 13 and 14 folder. And what I've got in there is I've got what I'm calling sample spaces. Okay, we said that one thing that's problematic is saying what the sum of two dice is when you roll it. And so what we have to do is we have to rethink our sample space so that everything is equally likely. And right at the top of our sample space, we have rolling two dice. And in our rolling two dice, what we've done is we've said, instead of looking at the sum, which we have down below here, okay, instead of looking at the sum, because you have a better chance of getting a 7 than a 2, I'm going to think of what's happening with those two dice, and I'm going to think of, them being separate dice, dice 1 and dice 2, and I'm going to put those together in an ordered pair. So dice 1 could be 1, or 2, or 3, or 4, or 5, or 6. And dice 2 could be 1, 2, 3, 4, or 5, or 6. And there's actually 36 ways that you could have those dice show up. And so by writing this out, we now have all of these things in here being equally likely. And so that's the sample space we're going to want to use. All right. Similarly, if we're dealing with tossing coins, you could say if we're tossing 3 coins, you could say all heads, all tails, 2 heads, a tail, 2 tails, a head, but those aren't equally likely. So we have to rethink how we toss the coins, and if we write it out in this way, now we've got stuff that's equally likely. So hopefully this sample spaces page is helpful to you. I'd recommend just printing it out, and as you work through the problems in this section, to go ahead and keep that handy. All right, let's go back to our notes here. And the next thing I want to talk about is what are the basic properties of probability. And there are 3 basic properties of probability. The first, we talked about a little bit earlier. We said that the probability of some event is always going to be less than or equal to 1 and greater than or equal to 0. And if the probability of some event is equal to 0, we say it never happens. And if the probability of some event is 1, we say it, probability of some event is 1, we say it always happens. Okay? Now the last thing we want to talk through as we get through these basic ideas is the idea of odds. And there's 2 kinds of odds that you can look at. The first, and the one that's used most often, is the odds against. And people get odds and probability mixed up quite often. But there is a relationship. The odds against something happening are the probability of that not happening. So the probability, the odds against, say, event E, are the probability that E doesn't happen over the probability that E does happen. Or, another way to say that is that the odds against are the number of ways E doesn't happen over the number of ways E does happen. And we can kind of see that from up above. If I was to rewrite this, not E would be the number of ways that E does not happen over the number of ways that the sample space can happen over the number probability of E, which is the number of ways that E can happen over the number of ways the sample space can happen. And when we simplify this fraction, those will cancel out, and that's what we get. So that's odds against. You could also talk about the odds for E happening. And that's really just going to be the flip of what we have up here. It's the probability of E over the probability of E not happening. All right? So those are all the definitions and the basic ideas that we need to talk through. Now I just want to look at some examples and see if we can figure out how this works in a little more detail. So the first example is we want to select a card at random from a 52-card deck. What is the probability that we will draw a face card? So if I go back to my sample spaces page here, I'm looking at playing cards. And here's my 52-card deck. And I have red cards, which are made up of hearts and diamonds, and I have black cards, which are spades and clubs. I have ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king. And our face cards are considered the jack, queen, and king. So if we look at how many face cards we have 3 hearts, 3 diamonds, 3 spades, and 3 clubs. So we have a total of 12 face cards out of those 52 cards. So that allows us now to go back and figure our probability, because we say that the probability of drawing a face card would be the number of ways that you can draw a face card over the number of ways that you can draw a card in general. And there are 52 cards in that deck. And of those cards, we had 12 that were face cards. So our probability of drawing a face card would be 12 out of 52. Notice we could simplify that down to 3/13, because they both have a 4 in them. Typically, when you're asked for answers in MyMathLab, you'll be asked for simplified fractions. So you're going to want to remember how to do your simplification. Now, let's take that and let's now answer the question, what are the odds against drawing a face card? Well, the odds against are going to be the probability of not pulling a face over the probability of pulling a face card. The probability of not pulling a face card is going to be, well, let's see, our probability of drawing a face card is 3 out of 13. So there must be, it would either be face or not face, and they should add up to the whole sample space, which is 1. So if we go back and look at it, we should have, if there's 12 face cards, there should be 40 non-face cards. Okay? And that would simplify down to 10/13. So our probability of not drawing a face would be 10/13. Our probability of drawing a face would be 3/13. Okay? And those would cancel out and leave us with 10/3. Or you can write it as a fraction, like that. So our odds against pulling a face card are 10/3. That means if we do the experiment 13 times, 10 times we should pull a non-face card, and 3 times we should pull a face card. on average. Okay. You could also say, what are the number of ways to pull a non-face? That would be 40. The number of ways to pull a face, that would be 12. And notice that's going to simplify down to 10/3. Okay. You could either do it by looking at number of ways, or you could do it by looking at probabilities. Now let's go on to another example. And let's say if we toss 3 fair coins, what is the probability that we will get 1 tail and 2 heads? In order to do that one, I'm going to go back to my sample spaces page. And I'm tossing 3 coins, which would be right here. And I want to know the probability of getting 1 tail and 2 heads. So when we first look at it, how many ways could we toss 3 coins? Well, 1, 2, 3, 4, 5, 6, 7, 8. So that's our sample space size. There's 8 ways we could toss 3 coins. And of those 8 ways, how many have 1 tail and 2 heads? Well, these 3 right here. So our probability is going to be there's 3 ways that I can get 1 tail and 2 heads, and there are 8 ways that I could toss my coins. Alrighty. One last example, and those of you that have had or a couple more examples, sorry. I'm going to add a couple here. So number 4 says, in a town there are 1,512 people who support a new business coming to town, while there are 2,268 who don't support it. What is the probability that a person chosen at random will support the business? So probability of support. Well, that probability will be the number of people who support the business, which would be 1,512, over the total number of people. This is not the total number of people, that's the number who don't support. So to find the total number of people, we'd have to add those who support plus those who don't support. So our probability would end up being plus 2268, would end up being 1512 over 3780. And then we could simplify that, or we could turn it into a decimal. And if we turn it into a decimal, it becomes 0.4. Okay? So the probability of picking somebody at random and having them support the business would be 0.4. We could write that as 40%. Okay? Sometimes you'll see probabilities written as percents. Now, number 5. If 10 horses are racing and you randomly select 3 as your bet in a trifecta, and a trifecta means picking the first 3 places in the proper order, what is the probability that you will win? Assume that all the horses have the same chance of winning. Well, our probability of winning is going to be the number of ways that we can pick these horses correctly. So if they came in the order A, B, C, that's the only way that you're going to, that's the only way you're going to win that trifecta. So there's only one way to win that trifecta. Now, how many ways could those horses come in those different places? Well, if we go back and think about our counting stuff, we have 3 places the horses could come in. Alrighty, and the order is important. There's 10 horses that can come in first place. Once the horses come in first place, they don't come back around. So there's only 9 horses left that could finish in second, 8 horses that could come in third. And order is important, so I don't have to divide out the overcount. And this is just a permutation. 10, choose 3. And that's going to be 720. So our probability of winning would be 1 out of 720. Now our last example is one that you could see in a biology class if you took one. And it's something called Punnett squares, which is used when you're looking at genetics and those sort of things. And it says sickle cell anemia is a serious inherited disease that's about 30 times more likely to occur in African American babies than in non-African American babies. A person with 2 sickle cell genes will have the disease, But a person with only one sickle cell gene will just be a carrier of the disease. If two parents who are carriers of sickle cell anemia have a child, what's the probability of each of the following? What's the probability that the child will have sickle cell anemia? What's the probability that the child will be a carrier? And what's the probability that the child will be disease-free? And in order to find those, what we need to do is come up with a Punnett square. And the way that works is we take the mother and the father and look at their contributions to the child's genetics. All right? And each of the parents is going to contribute two pieces. All right? It says that they've got two sickle cell genes. All right? And if they are carriers, that means only one of them is the sickle cell anemia. All righty? So the way we write that is we'll say one is sickle cell, one is not for the mother. And for the father, we'll say one is sickle cell, one is not. All righty? Then we look at what happens. So, and the child gets one from each parent, and it's just at random. So if the child gets this from the father and this from the mother, they get a double sickle cell, which means that they have the disease. So anytime they have two sickle cells, they have the disease. If they get an S from the father and an N from the mother, they have an SN. Or if they get an N from the father or an S from the mother, they have an NS. And they could get an N from both of them. So notice there are four possibilities that could happen here. What is the probability that the child will have sickle cell anemia? Well, in order to have it, you have to have two sickle cells. So that's one way that they can get it out of the four ways that those genes could be distributed. What's the probability that they are a carrier? Well, a carrier only has one sickle cell, so these two are carriers, so 2 out of the 4, or we could say that's half the time. And then what's the probability that the child is disease-free? Disease-free means that they have no sickle cells, and that's 1 out of 4. All righty? So that is an idea as to what probabilities are and a basic introduction to how to use them in some simple cases. Hope that is helpful.